Hello. In this video, I'm going to explain the energy graph for the mass that's thrown away from the Earth. The GP of the mass is of course given by negative gmm over r. So the GPE graph is the familiar 1 over x graph. So the GP of the mass is most negative when it started out at the surface of the Earth, and the GP of the mass is going to increase as it travels further and further away from the Earth. Actually, this graph extends in all directions from the center of the Earth. So it doesn't just go rightward, it also goes leftward, and in fact it also comes towards you, and it also goes into the page. I'd like you to imagine that the gravitational field of the Earth forms what is called a gravitational potential energy well, and therefore, as the mass is moving further and further away from the Earth, it's actually sliding upward along the wall of this energy well. And therefore, as the mass moves away, it must be gaining GPE, and therefore it must be losing KE. But if we sum up the KE and the GPE anytime, anywhere, it should be a constant. Now let's suppose the GP of the mass when it's on the surface of the Earth is negative 60 megajoules, and the mass is thrown at such a speed that it started out with a total energy of negative 20 megajoules. Now remember, the total energy of the mass is going to remain constant as it moves outward away, and therefore the total energy graph is a horizontal line. And something special happens here. At this point, the total energy of the mass is exactly the same as the GPE of the mass, which means the KE of the mass at this instant must be 0. So this is the quack 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 moment when this mass has slowed down and slowed down and slowed down and has come to a complete rest here. So from this point onwards, the mass is going to make its return journey back home to Earth. So this is the furthest the mass will get away from the Earth. We can also sketch the KE graph of the mass. The mass must have started its journey with a KE of 40 megajoules. This is because negative 60 megajoules of GPE plus the 40 megajoules of KE will give us the negative 20 megajoules of total energy. So as the stone moves away from the Earth, it must be gaining GPE, and therefore the KE must be dropping, because the gain in GPE comes at the expense of the loss in KE. So the KE graph is going to drop at the rate at which the GPE graph is rising. So these two graphs are mirror images of each other. So as can be seen clearly, this is the point where the KE is 0. This is the quack 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 moment when the mass has come to a rest, and from this point onwards, the mass is going to make its return journey home. So obviously, if this mass was projected with an initial KE of only 20 megajoules, then it would have started its journey with only negative 40 megajoules of total energy, and the total energy is going to remain constant, and therefore this is the furthest it will ever get from the Earth, and this is the quack 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 moment when it makes its return journey home. So what must the initial KE of the mass be such that it can totally escape from the Earth forever and never come back? Surely it is 60 megajoules of KE, because if you start off with 60 megajoules of KE, your KE is going to drop to 0 only at the point at infinity. And that means you have to start with a total energy of 0. Alright, that's all. Ta-ta!